we have learned several limit theorems, especially central limit theorems, which deals with convergence in distribution of a sequence of random variables or random vectors. But the question is, why do we study this CLT or this group of or a bunch of CLTs, both with respect to univariate as well as multivariate distributions? The thing is that, so today we are going to discuss some applications of this CLT, but before that, in order to do that, we need to understand a very important concept which we can use in proving several results. These are called order in probability. So, first we are going to define what is the meaning of order in probability, or rather first we will define what is the meaning of order in the context of sequence of real numbers. From there we will extend this concept to define order in probability. Later on we will see that this concept is extremely important in proving several theorems, and the proofs becoming very easy if we directly use this new concept of order or order in probability. In the first part we will discuss one important concept which we call order, and this order is usually denoted by big O and small o. So, later on you will you will see that this big O and small o, this jargon is coming very frequently, and this order is with respect to a particular sequence of variables, may not necessarily random, but when we deal with, because in statistics in probability we mostly deal with the sequence of random vectors, so naturally probability comes into the picture. So, a natural extension of the concept that is defined by calling order or capital O and small o, that should have been extended in case of order in case of probability. So, we define here as order in probability, which is denoted by big O of p suffix p and small o of p. We are going to define what is the meaning of these notations big O and small o, or big O p and small o p. First, consider a n to be an infinite sequence of real numbers and g n be a sequence of positive real numbers. First definition is that a n, sequence a n is of smaller order than g n, and we write a n equals to small o of g n if limit as n goes to infinity a n by g n equals to 0. So, this is denoted as a n equals to small o of g n, and whenever we write, we should think in terms of the ratio of this a n by g n, and if this limit goes to 0 as n goes to infinity, we say that a n is of smaller order or small o of g n. The second definition should be obviously with respect to big O. Here we say that the sequence a n is almost of order g n, and we write a n equals to big O of g n if there exists a real number capital M greater than 0, such that modulus of a n by g n less than equals to m for all n greater than equals to n dot. So, here we see that a n and g n are of almost of same order. That is why we denote this by a n equals to big O of g n. Then, since we have now idea about what is the meaning of small o and big O, naturally we can discuss or we can investigate various results with respect to this new concept. So, let a n and b n be real sequences and f n and g n be positive real sequences. Then we can prove a number of things. First is that if a n is of order small o of f n and b n equals to small o of g n, then a n into b n is again of smaller order f n g n. That means a n b n equals to small o of f n g n. Similarly, modulus of a n to the power r equals to small o of f n to the power r for r greater than 0, and a n plus b n equals to small o of maximum of f n and g n. Now, with respect to big O, we can think of another series of results which is given in B, that is, if a n equals to big O of f n and b n equals to big O of g n, then similarly as above we can immediately write that a n b n equals to big O of f n g n modulus of n to the power r equals to bgo of fn to the power r for r greater than equals to 0, and n plus bn equals to bgo of maximum fn gn. Now, naturally the question will arise that one series of results is only with respect to small o, and another series of results is only with respect to big O. So, can we have some result that is relating to both big O and small o? Fortunately, the answer is yes. So, the C part gives us this kind of result, like involving both big O and small o. That is, if n equals to small o of fn and bn equals to big O of gn, then n into bn equals to small o of fn gn. Now, let us see how to prove this lemma. But before that, we should remember that this order in probability was introduced by Mann and Ward in 1943, and that really revolutionized the proof of and the concept and the proof of many results in probability theory, and the proof of this result has become very easy. So, this proof we are not going to discuss, but it is immediately clear that if we consider the sequence of real numbers from our real analysis area, the proof would be pretty obvious. We have to write little epsilon delta definitions, and the proof becomes very obvious. So, from now on, whenever we want to prove something with respect to the sequence of real numbers, we can directly use big O and small o and use the previous series of results in order to prove some other results or theorems. Now we are going to define order in probability. So, let us assume that xn be a sequence of random variables and gn be a sequence of positive real numbers. Now, remember, this gn is not random, but xn is random. So, the third definition we can give, that xn is of smaller order in probability than gn. We can write capital Xn, this is the random variable or the sequence of random variables, capital Xn equals to small o p of gn if capital Xn by gn converges to 0 in probability. Because if we recall that if we drop this p, then there is no p, and this xn by gn should goes to 0 provided xn is a sequence of real numbers. Now, since xn is a sequence of random variables, then simple limit has no meaning. So, we have to consider limit with respect to probability or the probability limits, and that is why we are defining that xn equals to small o of p of gn if xn by gn goes to 0 in probability. And naturally, with respect to a big O or order big O, we can define that if xn we call a sequence of random variables xn is almost of order gn in probability. This is very important, in probability, and write capital Xn equals to big O p of gn if for every epsilon greater than 0 we can find one capital M greater than 0 such that probability modulus of capital Xn greater than equals to m into gn, which is less than epsilon for all n greater than equals to n naught. That means, given this epsilon, we can find some capital M as well as n naught such that probability modulus of x greater than equals to m gn, or we can write modulus of xn by gn greater than equals to m less than epsilon. Just one small note is that xn equals to OP of gn means xn equals to capital OP of gn, just the same order. And more generally, for two sequences xn and yn, the notation xn equals to big O of yn denotes xn by yn equals to big O of 1. Another notation, xn equals to small o p of yn denotes xn by yn goes to 0 in probability, and xn equals to small o p of yn implies xn equals to big O p of yn. So, these things are coming very naturally, is not really very difficult, but extremely important in order to prove several theorems and results that we will see later. Now, we are moving into defining this order with respect to random vectors. First, assume that xn is a sequence of k dimensional random vectors, and we say xn is almost of order gn in probability, and write xn equals to big O p of gn if for every epsilon greater than 0 there exists m epsilon greater than 0 such that probability modulus of x jn, now x jn is the jth component of the sequence xn, greater than equals to m epsilon gn, which is less than equals to delta for j equals to 1 to k. So, this is how we define in big O or order of almost same order as that of gn for a sequence of random vector. Next, we can again extend this idea to define the same kind of order with respect to a matrix, which is defined as a k by r matrix Bn of random variables. That means, every element of this matrix is a random variable, is almost of order gn in probability, and write Bn equals to big O p of gn if for every epsilon greater than 0 there exists m epsilon greater than 0 such that probability modulus of b I j n greater than equals to m epsilon gn less than equals to epsilon. We can use delta here, but it is okay if we use epsilon here also. For I equals to 1 to k, j equals to 1 to r for large n, where b I j n are the elements of Bn. So, here we have seen that first we have defined this order big O for a sequence of real numbers. From there we have extended it to define order in probability, that means big O of p with respect to a random variables which is univariate, and then again we extended it for k dimensional random vector, from which we again extended this to a random matrix of arbitrary order. Similarly, we can define smaller order in probability, that is small o of p for random vectors as well as for random matrix Pn. Now, another set of important results. Let xn and yn be sequences of random variables, and fn and gn be sequences of positive real numbers. If capital Xn equals to small o p of fn and yn equals to small o p of gn, then xn yn equals to small o p of fn gn, modulus of xn to the power r equals to small o p of fn to the power r for r greater than 0, and xn plus yn equals to small o of p of maximum of fn gn. It is clear that we have already seen the same kind of results in case of real numbers, sequence of real numbers, but since here we have introduced order in probability, we are going to give outline of the proof, because this is little bit technical, not definitely very difficult. So, first to prove that xn yn equals to small o p of fn gn, we choose an epsilon and fix that epsilon greater than 0, then naturally there exists delta greater than 0 such that probability modulus of xn greater than epsilon fn is less than delta by 2, and probability modulus of yn greater than epsilon gn less than delta by 2 for n greater than equals to n naught, because we know that xn equals to small o p of fn and yn equals to small o p of gn. Then we have to show that modulus of xn yn, or rather xn yn equals to small o p of fn gn. So, we start with the definition like probability modulus of xn yn greater than epsilon square fn gn. We have to show that this probability less than an arbitrary smaller number. Now, this quantity is less than equals to probability modulus of xn by fn greater than epsilon, or modulus of yn pi gn greater than epsilon. It is clear this left hand side, the event in the left hand side always imply this right hand side events. Again, the right hand side being the union of two events, it is always less than equals to sum of the probabilities of these two events. That means, this is less than equals to probability modulus of xn by fn greater than epsilon plus probability modulus of yn by gn greater than epsilon. And from the given condition, this sum is definitely less than delta whenever n greater than equals to n naught. So, that that actually proves the first result. To show that the second one, that is modulus of xn to the power r equals to small o of p fn to the power r for r greater than 0, whenever modulus of xn or equals to small o p of fn, we can see that probability modulus of xn greater than epsilon fn, which is equals to modulus of xn to the power r greater than epsilon, it should be epsilon to the power r fn to the power r, but we can use epsilon as a generic small number. So, epsilon to the power r is very small. So, we can take this as just a notational convenience, we can write this as epsilon, and this is true for every epsilon greater than 0. So, it is clear that since we know that probability modulus of xn to the power r greater than epsilon fn to the power r, which is extremely small, this probability, then modulus of xn to the power r equals to small o p of fn to the power r for r greater than 0. Now, to show the last result, that is sum of the sequence of random variables, that is xn plus yn equals to small o p of maximum of fn gn, let us write qn equals to maximum of fn gn. Then we have for a fixed or given epsilon greater than 0 and delta greater than 0, we can always find an integer n such that probability modulus of xn greater than epsilon qn by 2 less than delta by 2, and the same thing, that is probability modulus of yn greater than epsilon qn by 2 less than delta by 2 whenever n is greater than equals to n naught. So, now probability modulus of xn plus yn greater than epsilon qn, which is less than equals to the sum of previous two probabilities, that is probability modulus xn greater than epsilon qn by 2 plus probability mod xn mod yn greater than epsilon qn by 2, and naturally which is less than delta whenever n greater than equals to n naught. So, this proves the third result also. So, the proof is exactly in the line of the proof in case of real analysis, but we have to consider the probability and hence the probability of each event. The next series of results should be with respect to BGO. So, let xn and yn be sequences of random variables and fn and gn be sequences of positive real numbers. Now, again exactly like the previous series of results, if xn equals to BGO p of fn and yn equals to BGO p of gn, then we have xn yn equals to BGO p of fn gn, modulus of xn to the power r equals to BGO p of fn to the power r for every r greater than 0, and xn plus yn equals to BGO of p maximum of fn gn. And another series of results that involves both BGO and small o, which is extremely important, that is if xn equals to small o p of fn and yn equals to BGO p of gn, then modulus of xn yn equals to small o p of fn gn. We are not going to prove this directly, but the proof of this, all these results follow the same technique that we have used in proving lemma 2. So, this gives us a very good idea about how to use BGO and small o, not only in case of sequence of real numbers, but also considering the order in probability, that is BGO p and small o p in case of a sequence of random variables. So, today's talk is little bit technical in the sense that we have defined a new concept which we call order in probability, and we have seen that we have derived many results, many important lemma or theorems using this concept of order. We have also seen that we have used this order can be applied not only to a sequence of univariate random variables, but also to a sequence of multivariate random vectors in order to investigate several large sample properties or limit theorems with respect to these random variables or random vectors. So, this concept or this idea, although it seems to be little new and little technical, but it is extremely helpful in proving many results in this area.